Okay, so I see we're at the 40 mark here. So at this point, I'd like to thank all the discussants and authors, and we can move on to the poster pitches. Since we are running a little bit behind schedule, I would ask that that each pitcher keep their presentation to 1 minute and 3/4 instead of the 2 minutes. And we'd also like to invite somebody who wasn't able to present yesterday, but we'll have them present at the end. So I'd like to invite the first poster, combining data-driven and knowledge-based AI paradigms for engineering AI safety critical systems. So is an author for that here?
Yes, I will share my screen. Did you see the screen?
Yes, we can see it.
Okay, so good afternoon, everyone. I will present very briefly the work done with my colleague Gabriel, Seán, and Bertrand in the context of Confiance.ai. As you know, if we want to deploy AI in safety critical systems, we face two various engineering challenges. For example, we have to demonstrate the correctness and the validity of our AI-based system by proving that the AI components does what it is supposed to do, all what it is supposed to do, and only what it is supposed to do. And as most time we have a human in the loop, we have to provide means for interpretability and explainability. Finally, as we are in the context of safety, we have to deal with robustness with respect to user usage, but also to adversarial condition. Moreover, as explained before, Confiance.ai address also all AI discipline, not only data-driven AI, such as machine learning, but also symbolic AI and hybrid AI. To reach our objective, we have to revisit all engineering activities in order to propose methods and tools to support a sound deployment of AI in critical systems. To do that, we first define a trustworthy AI engineering analysis framework to formalize all engineering activities and roles in order to propose a first end-to-end engineering workbench based on combining data-driven AI and knowledge-based AI paradigm in order to assess risk and to demonstrate safety properties through assurance case. To conclude, we propose this year a first instance of this workbench dedicated to machine learning algorithm engineering, enhanced by a trustworthy AI engineering taxonomy enriched with trustworthy characteristics and KPI.
Thank you so much. We'll move on to the second poster. Is it all a cluster game?
Hi, can you hear me?
Yes.
My slide is visible?
Yes, it is.
Okay. Good afternoon, everyone. Today, I would like to present our work on exploring out-of-distribution detection based on clustering in the embedding space. So the primary motivation is, can we learn to use clusters of semantically similar data to distinguish between in-distribution and out-of-distribution samples? And for this, we have used methods like contrastive learning, which basically clusters similar instances and classes together, and at the same time pushes apart dissimilar instances or classes. For this work, the methods used are SupCon and SimCLR, which are respectively supervised and self-supervised methods, and compared with cross-entropy as baseline. So once we have a contrastively trained model, we want to analyze how good the cluster formations are. And for this, we have used metrics like global separation and cluster purity, and for which we have some interesting results which can be referred into the paper. So the next section, I would like to introduce the cluster analysis itself for OOD detection. And for here, we have inspected into 3 different scenarios. First scenario is where the ground truth class-based clusters are taken. And the second scenario is where the entire cluster is taken as a whole. And the third scenario is where we further do clustering on the learned embeddings using Gaussian mixture model or k-means. Now we apply distance-based metrics like cosine similarity and Mahalanobis, and then we further use these distances as to evaluate the evaluation scores, which is ROC. And this is done also for individual clusters and over the entire data set, which is the global score. For this, we have different trend plots, as you can see, and this is way too elaborate to discuss over here, but to keep it in a brief, we see that for different methods like cross entropy and SubCon and SimCLR, the Mahalanobis scores continue to decrease from cluster size 1 to further when it's further increased, whereas the cosine scores continue to increase. And there is no clear winner on each of these plots. So what we definitely understood is that supervised methods have much better clusters in the embedding space, like clear distinct clusters, whereas the self-supervised methods like SimCLR have overlapping clusters. And while there is no winner, we could also say that cross-entropy based methods, which are less expensive than contrastive learning methods, also provide competitive results. Thank you for listening. And if you have any further questions, please feel free to ask me.
Thank you so much. We'll be moving to the third one here, a overview of safety concerns and mitigation methods for visual deep learning.
Okay, can you hear me?
Yes, we can hear and see.
Great. So, my name is Said, and I will be presenting my work on a practical overview of safety concerns and mitigation methods for visual deep learning algorithms. The general idea is to have the practical side of the machine learning while trying to develop some algorithm for safety critical application. And the objective is to categorize faults and their underlying causes in a visual deep learning algorithm in order to provide a practical list of all safety concerns and potential existing mitigation methods to deal with these problems, and then discuss the effectiveness of these existing mitigation methods and whether we need further research or not. And here you can see a list of the categorical safety concerns that we found so far. So it all relates to either data set, the architecture, and the testing phase of the using metrics, proper metrics and benchmarks, or the inherent nature of the machine learning, which has the black box behavior, or finally, the environment and the hardware itself. And you can find more information about each individual safety concern in the paper, and the mitigation methods that exist are also mentioned there. But in conclusion, in what we found is the state-of-the-art mitigation methods all have vital drawbacks. It's always a talk of accuracy versus safety, or demanding high resources or high time of working, or requirement of expert knowledge. And while some of these mitigation methods can be used properly in current systems, most of them cost a lot and might not be practical. So multiple scenarios require further research at this point, and maybe it's time to move away from traditional broad spectrum safety standards towards some task-specific standards. And that's our paper so far. Thank you for your attention.
Thank you, Said. We'll move now to a framework to argue quantitative safety targets in assurance cases for AI/ML components, combining design and runtime safety measures. Is an author for that here? If not, we'll move to the last one, which is one from yesterday, who was unable to present, Sheila Alamani.
Hi, let me just. Can everybody see my screen okay?
Yes, we can hear and see you. Thank you.
Okay, great. So hi everyone, I'm Sheila Lamani. I'm a PhD student from Florida International University, And today I'm going to quickly talk about our recent work on the dilemma between data transformations and adversarial robustness. So this work aims to explore whether any data transformations are being used for performance outside of the context of robustness are unknowingly resulting in accidental vulnerabilities on deployed models. So to explore this, we looked at 3 classes of data transformations, specifically dimensionality reduction, feature selection, and trend extraction techniques. And we looked at it from the perspective of the data manifold to understand how changes in the embedding space, so the data, may impact the resulting data manifold, which is what is created by the trained machine learning model. So we observed that the ideal scenario where robustness is improved is only when the codimension, which is the difference between the embedding space and the data manifold, is minimized. And this doesn't necessarily happen with all 3 different data transformation classes. So for example, trend extraction techniques like the data stick candle structure, the candlestick data structure, it's used in economics often, and it results in information loss that can result in an increased vulnerability. So similarly with some feature selection techniques that can happen, but to a lesser extent. Additionally, with dimensionality reduction, we observed that keeping a high dimensionality is not great. And this is consistent with what we know about robustness to date. But more interestingly, we saw that reducing the dimensionality too much was also not ideal for robustness because of the data manifold's lack of coverage of the general embedding space. So overall, we observed that the difference between the embedding space and the data manifold was minimized when the specific transformation approached this intrinsic dimension. And this intrinsic dimension is the minimum number of variables or features needed to describe a dataset's distribution. So overall, it is possible for data transformations to introduce vulnerabilities through certain data transformations. So ML practitioners have to observe and understand a particular dataset's intrinsic characteristics to avoid this. Thank you.
Thank you so much, and thank you all in this session.
Excuse me, I guess that you missed my poster, Michał Filipiuk comparing vision transformers and convolutional nets.
My mistake. I apologize.
Yes. Yeah, I didn't want to mention it earlier, but as we are finishing and I'd like to show it. Yeah, that's why I'm here.
Yes, I thought I did a call for that before, but I could be mistaken.
Yeah, I think also the poster about the framework for accurate quantitative safety target is missing yet.
Well, we did a call for that, but we didn't hear an author. But I see that you are an author, so yes, we'll certainly have you go as well. So yes, Michał, yes, apologies. Please
okay.
Present.
Just a second. Okay.
Okay, then I would start. So for background, for the acceptance of an AI or AI-enabled system, it's not only important that it's sufficiently safe, but also that we can convincingly show this fact. One option for achieving this, which is also strongly discussed in standardization and research, is the use of structured assurance cases, as we heard in the morning. Assurance cases have long been used in safety engineering as a method of incremental decomposing claims into subclaims, for which evidences then can be provided. In practice, however, we need not only a general method, but also some concrete patterns that tell us how to structure an argument for AI-enabled systems. So one suggestion is to argue using complementary risk acceptance criteria. Here, in a first line of argument, we need to show that we did everything that is reasonably practicable to reduce the safety risk of the AI component, considering the different life phases. However, doing everything that is reasonably practical is not always sufficient. Therefore, in a second line of argument, we need to demonstrate that the AI component satisfies some given quantitative goals regarding the probability of safety violations. Today, this quantitative line of argument often exclusively considers test results. In our view, this simple approach usually falls short in practice, however. As part of the specification, we should at least additionally consider the probability that the system will operate outside its target application scope and how likely it is that we can detect this. In addition, even if we do our best, data sets, including test data sets, are never error-free. Therefore, the probability and impact of wrong labels should equally be considered. And finally, required safety-related failure rate cannot always be demonstrated exclusively through testing. In this case, uncertainty predictions at runtime can be used to detect situations with a high risk of safety failures in order to treat them separately. This reduction of the safety load achieved should, of course, then be also taken into account. If you're interested in what such a quantitative argument can look like, you will find our poster and more details in the report we linked there. Thank you.
Thank you, Michael. Now, Michal Philippou.
Yes, I just need to wait for Michel to finish presenting it. Now I can share my screen. It should be visible now, right? Right. Okay. So hello everyone, my name is Michał Filipuk and I'll talk about leveraging vision transformers to increase the robustness of safety critical systems. Vision transformer is a new kind of architecture using self-attention operation instead of convolution, which is applied over non-overlapping patches of the input image. There is multiple research results showing a few key properties of vision transformers. Reusability, transformers perform as well or better when fine-tuned to new tasks. Robustness, transformers are at least as fast as CNNs regarding common corruption. Detection of distribution shift, transformers perform better in detecting out of distribution samples. And redundancy, transformers and CNNs learn differently, what's reflected in their internal structures after training. We check whether combining these two architectures can improve the common corruption robustness on ImageNet C dataset. We take big transfer and vision transformer models, and we create the ensemble by multiplying their softmax outputs. As we see in table 2, this ensemble can perform better or comparably to single models, which is expected. What is interesting is contrast and fog corruptions. Here, one model performs significantly worse than the other, but ensemble manages to stay on top of both, combining robustness of the models. These results are just a proof of concept. We plan to conduct a broader research involving multiple models. It would also be worth to try how this robustness would look like for object detection or image segmentation problems. I'm really sorry, I just clicked escape. Just a second, and we are back. Apart from robustness, diving deeper into out-of-distribution detection using transformers looks promising, or how to efficiently use transformers in resource-constrained systems. Thank you very much. I hope you find it interesting and inspiring. If you have any questions, please reach out to us at the poster exhibition. Thank you.
Awesome. Thank you so much. And now thank you to everyone, and apologies for missing posters there. All right, so with that, we will reconvene at 15:20 UTC. And of course, we have the poster exhibition now, in addition to coffee break. All right, so thank you all.